Welcome AP Chemistry students to Unit 9, Applications of Thermodynamics, our final unit of AP Chemistry. Congratulations, you've made it here. Now, we have already discussed thermodynamics, the laws of physics that govern energy within the universe. So today we are going to review some of the concepts we've already talked about, as well as introduce something new. So remember, when we talk about thermodynamics, we are talking about energy, and from 8th grade you've learned about energy before. Kinetic energy is energy of motion, and in chemistry it is most proportional to the temperature, specifically the temperature in Kelvin, right? So if something is at 400 Kelvin, that has more kinetic energy than something at, say, 200 Kelvin. We can look at this kinetic energy on a Maxwell-Boltzmann distribution, which shows the number of particles at different speeds. So of these two systems, T2 represents a higher temperature because there are more particles at a higher speed. Maxwell-Boltzmann distributions are relatively new on the AP exam, but the questions that are asked are fairly simple as long as you keep in mind that they show the number of particles versus their kinetic energy or movement. So in example 1 in your packet, it says, here are 3 systems. Which one produces the most products and why? Well, for each of these systems, the energy those molecules have has to overcome the activation energy for the reaction. You remember activation energy on a potential energy diagram. The activation energy is the amount of energy your reactants have to have in order to form products. We'll talk about them, we'll review them in just a second. But in order to form products, our reactants have to collide with a certain amount of energy. So if we were to put the activation energy of a reaction, so let's hypothetically say this reaction had an activation energy of 5 megajoules. System 1 is going to produce no products because none of the molecules have enough energy to overcome that activation energy. System 2 is going to produce some products because the area under the curve after the activation energy does exist. There are some molecules that have enough energy to form products. However, that number is significantly less than System 5, which has lots of products that will be produced because all of these molecules are moving fast enough to overcome the activation energy. So the area under the curve for System 5 is the highest. Now, the amount of energy your reactants have to have when they collide to form products is their activation energy, normally seen on a potential energy diagram. In physics, you learned about potential energy as energy of location. Potential energy in chemistry is stored in bonds, and it's often referred to as the heat or enthalpy of that system. And we've talked about these as joules or calories, but the enthalpy or the potential energy of a reaction as it occurs is the difference between the enthalpy of your reactants and the enthalpy of your products. So the difference between your reactants and products gives you the enthalpy or the heat of a reaction. Your reactants have to collide with enough energy and in the correct orientation to form those products, so the amount of energy your reactants have to gain to overcome their intramolecular forces to become those products, to reshape, is known as the activation energy. We've covered all of this before, so if you are a little shaky on some of these, please go back to Unit 6 and review enthalpy as well as collision theory. For right now, just remember that when it comes to calculating enthalpy, we did it a number of ways. Yes, the difference between reactants and products, either forming an exothermic reaction as your reactants lose energy to form products, or endothermic as your reactants gain energy to form products. We could look at the potential energy diagram, but we also calculated enthalpy a number of ways. Stoichiometrically, when we have a reaction, where you could be given the enthalpy of a reaction, that is for each mole of reaction. So for the reaction here, if the heat of the reaction is 20 kilojoules for each mole of reaction, that means 20 kilojoules is a reactant, and you can treat it as such stoichiometrically. If it were an exothermic reaction, if enthalpy were negative, it would be a product, and again, you can treat it stoichiometrically, where 1 mole of A would make 20 kilojoules of energy, while 2 moles of A would make 40 kilojoules of energy. We also calculate enthalpy using calorimetry, where Q equals mc delta T, because the energy transferred is equal to the enthalpy as long as pressure is constant. So you can use Q equals mc delta T if you were dealing with energy being transferred into or out of a system. We also used heat of formation tables, where we were given the amount of energy it takes to form a substance, and we took the sum of the heat of formation of our products and subtracted the sum of the heat of formation of our reactants from it to get the heat of the reaction. The only thing here was to remember that anything elemental had a heat of formation of 0, because we're not going to form elements. All the elements are already formed, so the amount of energy it takes to form them is nothing. Along that same lines, we also calculated enthalpy using bond energies, where our reactants would need to be broken, which requires energy, and our products need to be formed, which releases energy. So we simply assigned each of them a sign and added them all up. Lastly, we calculated enthalpy using Hess's law, which, remember, you were given a string of reactions and you had to put them in order to canceling out intermediaries and catalysts to get the sum of all of the energy given. In today's lessons, we're going to use a lot of these systems again as we calculate something related to enthalpy, to potential energy, the entropy of a system. Entropy is a measure of randomness, of the different quantum states that a system could be in. From a simple standpoint, think of it as movement. A substance with lots of movement has lots of different states its matter can be in. So, a gas where the molecules have no intermolecular forces and therefore are free to move as much as possible has a massive amount of entropy. But if you were to remove some of the energy from a system and cool that gas down till it formed a liquid, that would be less entropy. If you were to remove even more energy and the system took on a crystalline lattice, those molecules can't move, they are held in place, so solids have the least amount of entropy. Aqueous systems have more energy than a liquid because a pure liquid will have only one type of molecule or atom in it, while aqueous solutions have other things dissolved, different systems with different amounts of entropy involved in them, so they move more. So you can look at entropy from a state of matter standpoint. On an even deeper level, you can look at the number of electrons an atom has. If I have an atom of hydrogen, its electrons can be on the left, the right, the top, or the bottom. It only has one electron, so that's substantially less entropy than, say, an atom of helium, which has 2 electrons. They could both be on the left, they could both be on the right, they could be separated. But you see what I'm getting at? The more electrons you have, the more entropy there is. So, let's tackle the easier way of thinking of it. Let's look at just states of matter in example 2. Here are some example multiple choice questions taken from old AP exams. Which system has the largest increase in entropy? So for number A, I have 2 gases that form 2 gases. That's almost no change in entropy. There is some, because elemental chlorine and elemental hydrogen have different entropy values than hydrochloric acid. However, generally, from a state of matter standpoint, that's not going to show the biggest increase. So let's look at letter B. I have 1.5 gases that form a single gas. I have more gas that's being condensed into less, so this is actually a decrease in entropy. So neither answer A or B is a very good one. Let's look at example C. I have a solid and a gas that forms a solid. That's also a decrease in entropy, but it's a lot more than the one before, where I have 1.5 gases that becomes a gas. That gas is still going to have a lot of entropy, but if I have a solid and a gas that becomes a solid, that's a lot less entropy. That matter is far more ordered. So I'm just going to make a note to myself, like, this is a big negative. We're looking for a positive, so answer C is also out. So let's hope the answer is D. I have a solid that forms 1, 5, 6 different gases. That is a huge increase in entropy, where a solid, lots of order, breaks down into all of these different gases. The answer choice that's best for exercise 2, number 1, is A. Why don't you pause the video and go the other direction? Which of these shows the biggest decrease in entropy? Again, the best answer choice is D. As letter A is 3 gases becomes 2. That's a drop in entropy, but you still end up with a gas. In the answer D, you have a solid and 3 gases that become no gases and just a solid. That's a huge drop in entropy. So for both choices, the best answer is D. In example 3, it's more like a free response. On a free response question, you might be asked, hey, you have solid sugar, it's added to water to form a solution. Predict the sign of entropy. Is it positive or negative? This is going to increase in entropy. Because as a solution, the sugar is now mobile and no longer in a crystal lattice. If I have iodine vapor that condenses to form crystals, this is a decrease in entropy, because mobile gaseous iodine is now held in a crystalline solid lattice. And when we go to calculate entropy, it's calculated the same ways. It is unusual for you to be given the stoichiometry method. However, it is possible, so just treat it the same way, but we're not going to do an example of that because, as I said, I haven't really seen that, but I do know that it does exist. What you are most likely, the most common way to calculate the entropy of a system is through either tables, Hess's law, or bond energy. And we're going to do them the same way that we did enthalpy. So, starting with tables. Here we have the reaction of sulfur dioxide and oxygen to make sulfur trioxide. It is at a specific temperature because entropy is temperature dependent. At higher temperatures, things will move faster. That's more quantum states, and therefore entropy will be different at different temperatures. However, at 25 degrees, we are given the entropy values for everything. But Professor, oxygen is elemental. In enthalpy, anything elemental had a heat of formation of 0. Why does oxygen not have a 0 value here? Well, because oxygen contains those electrons, and they are in constant motion, so it has many different quantum states. Is this electron here? Is it in the bond? Is it on the other oxygen? Is it at the edge of space? No one knows, but it definitely has its own entropy value. So what's different between enthalpy and entropy, calculating delta S versus delta H, is that elemental substances will have a value for their entropy. They will have a delta S value. But that's fine, we just treat them like we do anything else. So to calculate the entropy change of this reaction, we'll take the sum of our products and subtract from it the sum of our reactants. So the entropy value of sulfur trioxide minus the sum of the entropy value of oxygen and sulfur dioxide. There are 2 sulfur dioxides and 2 sulfur trioxides. So keep in mind your stoichiometric coefficients. So 2 times 256.6 minus 205.3 plus 2 times 248. The sum of our reactants here is 701.5. Sum of our products is 513. And the change in entropy of this reaction is a negative 188.3 joules for each mole Kelvin. But does that answer make sense? We go from 3 moles of gas down to 2 moles of gas, so we would expect an entropy value that's negative. So this answer logically matches what we would expect. It's a good answer. We can use entropy to determine what temperature a phase change occurs at. Since it's in joules for each mole Kelvin, if I know how many moles of a substance I have and how much energy it takes to go through that phase change, simply putting temperature in the denominator will allow me to determine the entropy change for that reaction. Or if I know the entropy and how much energy it took to go through the phase change, I can tell you what temperature it occurred at. Since if phase change occurs at a constant pressure, we could replace the energy transferred with the heat of that phase change. Say we were evaporating something. So the heat of vaporization over temperature has to equal the entropy that changed. So if I wanted to know the temperature, I could multiply by temperature on both sides, giving me this expression. And if I divide by delta S on both sides, the temperature at which a phase change, or in this case vaporization, would occur would be to take the heat of vaporization and divide by the entropy change for that reaction. So if you're ever asked, hey, what temperature does a substance boil? If you have the heat of that phase change and the entropy, you can determine the temperature at which it boils. But we can also determine entropy simply by taking the heat of a reaction and dividing by the temperature at which that reaction occurs, which is what the next example has us do. We are given 2 reactions and we are asked to determine the entropy change for each one. So if I take each of these enthalpy changes and divide by the temperature, I'll get the change in entropy for each reaction. And then it's just a matter of adding them up if they're in the same process. Now there's one kicker here. Temperature has to be based on kinetic energy, based on that Kelvin. So 25 degrees Celsius is not usable. I need it in Kelvin. So for each of these, I'm not going to divide by 25. I'm going to divide by 298. So for reaction 1, I get a negative 0.419 kilojoules for each mole Kelvin. And for reaction 2, I get 2.6 kilojoules for each mole Kelvin. So the change in entropy for the whole process is 2.19 kilojoules for each mole Kelvin. So, if we want to know the temperature at which boron trichloride boils, we can determine that by taking the heat of the reaction and dividing by the change in entropy. So to find the heat of the reaction, we were given the heat of formations. So the heat of this reaction would be to take the sum of the enthalpy of the products and subtract the enthalpy of the reactants. So our products being gaseous boron trichloride has a heat of formation of a negative 395 kilojoules for each mole. And the heat of our reactants formation is a negative 418 kilojoules for each mole. So the change in enthalpy for this phase change is 23 kilojoules for each mole of boron trichloride. To find the entropy of this reaction, we'll simply take the entropy of our products minus our reactants. So 290 minus 209 gives us an entropy change for this reaction of 81 joules for each mole Kelvin. We are looking for a temperature, so when you divide by a fraction, it flips, giving us mole kelvins for each joule. Joules and kilojoules are not going to cancel each other out, so you do need to pay attention to your units. 81 joules for each mole Kelvin we would need in kilojoules. So since there are 1,000 kilojoules in 1 joule, if we divide 81 by 1,000, we get 0.081 kilojoules for each mole Kelvin, and therefore kilojoules will cancel out, moles will cancel out. We can determine the temperature at which this boils in Kelvin. 23 divided by 0.081 is 284 Kelvin, or approximately 11 degrees Celsius. And with that being said, that'll bring us to the end of Unit 9.1. I'll see you next time when we calculate if a reaction actually is thermodynamically favorable by determining Gibbs free energy.